Hello everyone, today I'm going to be showing you how to derive v equals u plus at by using the power of calculus. Exciting stuff. Now just for reference, it's this equation we are going to be deriving today by using calculus. Now this is the first part of kinematics in the advanced hard course. Hope you enjoy. Now let's take a look at some graphs here. So we've got displacement, velocity, acceleration time graphs. These should be very familiar. You've known them since National 5. Nothing really new here. Excuse me. Now, what you see here for the velocity and acceleration, we can use the Suvat equations here, which are these, to find out missing parts. Okay? So you should know what I'm talking about here. So you've got the straight line for the velocity time graph. So everything's good here. But what if we have a line like this for a velocity time graph? We can no longer use the Suvat equations. So we've got a bit of a problem here. Can't use the Suvat equations anymore. So we're going to have to use differentiation. You should be very familiar with differentiation. You should have done it in higher mathematics. So I'm going to draw a line tangent to the curve here. Oh, that's very off. Still off. There we go. That's good enough. That's good enough. So the line tangent here, let's just say it's tangent, I know it's not, but we'd find out the gradient at this point, and that would give us the acceleration at that point. Okay? Now to find out the gradient at this specific point, we would be finding out the instantaneous acceleration. Okay? And how we do that, we use differentiation, as I've repeated many times already. So in maths you will be very used to using dx by dy. Okay, this is Leibniz notation. But we don't have x and y anymore. We have different terms. We have dv by dt, and that will give you your instantaneous acceleration. Okay, so this is just partially why calculus is such a powerful tool. And we can also do the same for the displacement time graph. So if we have a tangent to the curve here, and we use differentiation again. Instead of dx by dy, it's ds by dt, which will give you your instantaneous velocity. Okay? So this is just the base for everything. And there's one more thing about the instantaneous acceleration. You may see it written like this: d squared s over dt squared. Now, I'll explain why it's like this right now. Just because it's something that the textbooks tend to skip over a lot, and I think, it's just one of those things that annoys me that they don't explain. Right? So, dv over dt equals a, and ds over dt equals v. Alright, you'll find these on your formula sheet, by the way. And the way we get d squared s by dt squared is very simple. For dv by dt, we need to pull this v out, right? So it gives d over dt times by v. Right, this is still all correct. We've just pulled the v out from the fraction. And we've got a separate term for v, which is this, ds over dt. So we can just replace v with ds by dt, which equals d over dt times by ds over dt. Right? And then that will give you d squared s over dt squared. Right, you've learned your first thing in physics. Congratulations. Oh, we're halfway there. Not really, but don't worry, it's not that bad. Anyway, so this is just something I need to get out of the way first. Now, how to derive the equation. So we know that dv over dt equals acceleration. Right? Now we're going to switch dt over to the other side. So we're going to times it by both sides. So that becomes dv equals a dt. Now this is a bit of a fun concept here, splitting apart the Leibniz notation. Okay, you haven't done this in maths before. Just go with me. Okay. Now we're going to take the integral now of both sides. Right. Not so bad if it's step by step. And now it can go one or two ways to derive the equation. I'm going to show you the first way now. So we're going to set limits for initial velocity all the way up until final velocity, because it's in terms of velocity here with respect to velocity. Okay? And we're going to set limits on the right hand side. So now that it's in terms of time, we have to set limits in forms of time. So we're going to start from 0, which is just t equals 0, all the way up until t. Right? With me so far? It's not bad. And then you do your integration thing, where actually on the left hand side there is a secret 1 here. Okay? And then if you integrate 1 with respect to v, you get just v. Right? And then with a, so a is like a number here. Okay? And when you integrate a number with respect to time, it's number time. So a t 0 t. Okay, still with me? Good. If you have any questions, post them in the comments. I'll be happy to answer them. Actually, it'll be one of the best things to do in lockdown. Right, so that becomes v minus u equals at minus 0. Right? Because we've expanded these brackets. Okay? And then v minus u equals at. And then, if we rearrange that, it becomes v equals u plus at. Wahey! We have the first equation. Well done us. And then I'll show you the other way now. So we're going back to dv equals a with respect to time. Sorry, I should say with respect to velocity and with respect to time. Sorry, that's a bad habit to get into, so don't start it. I'm warning you. So we're going to integrate both sides again. But we are not going to set limits this time, okay? That's important. So the secret one here, okay, so that just becomes v equals at plus c. Alright? So we have the constant of integration now, because there's no limits. And to find the constant of integration, we are going to set time to 0, so t equals 0. V equals a times by 0 plus the constant of integration. That means v equals c. Now, when time equals 0, the velocity will actually be the initial velocity. So c equals u. And if we input that back into here, we get v equals u plus at. There you go. 2 ways to derive the equation. V equals u plus at. Thank you very much. I hope you've enjoyed. I certainly have.